Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD heat transfer analysis through a cross-flow heat exchanger using ANSYS Fluent fault-tolerant meshing. This is the model, right? From left-hand side, we'll be providing cold water, and from this side, we will be providing hot air. And at the exit, we'll be collecting hot water, and at the right-hand side here itself, we'll be collecting hot air, right? This is the model. Inside this one, we're having a lot of copper tubes, and you can see here this side some gap is there. From this gap we'll be providing hot air, right? For understanding this model in a better way, let us cut this one from specific planes. Let us cut it from YZ plane. You can see this is the view. So cold water will be passing from the shell, and from this side we'll be providing hot air to increase the temperature of cold water, right? We need to save this model as FM database with the extension of FMD. We have already saved this one, so let us close it, and we have to start ANSYS Fluent fault tolerant meshing, and we need to start Fluent launcher. Let's start Fluent launcher. First of all, we need to select fault tolerant meshing from here, and then we need to import that CAD model from here. Let us import this model from here. We need to import with the custom mode on, and then we can load it. We need to drag this component into meshing model. Then with the advanced object settings, we need to create the zone as part. Then we should copy settings to child objects, and finally we need to create meshing objects. The object is being prepared for initiating meshing. You can see this is the object. Next to that, we need to describe the geometry and flow, and it is an internal flow analysis with the default setting on. With internal fluid flow analysis, we need to describe the geometry and flow. In CFD analysis, we need to create a closed volume. That's why all the openings should be closed. Here in this case, we are having 4 different openings, 2 inlets and 2 outlets that will be closed here. Let us open cold water inlet, and zone type will be in this case velocity inlet or mass flow rate. We can define this name as cap 1. Next to that, we need to create cap at the hot air inlet, and in this case also the zone type will be velocity inlet, and we can rename this one as cap 2. Let us create cap at the hot air inlet. You can see here cap is produced at hot air inlet. Now we have to create caps at the exits of cold water and hot air. First of all, we will select exit of cold water, and in that case zone type will be pressure outlet as it is the exit, and we are renaming this one as cap 3. It is done. You can see here cold outlet cap is produced. Finally, you need to create cap at the hot air outlet. Again, in this case also, zone type will be pressure outlet. We are renaming this one as cap 4. We can see all the caps have been produced, right? You can see this is a closed geometry right now. Now this is ready for the next operation, right? Next to that, we need to identify regions. That means we need to identify the fluid domains. In this case, we are having two fluid domains. One is cold water and another is hot air, right? These fluid domains can be identified using the different options like centroid of objects, or you can say numerical inputs or offset methods. We will consider offset method for locating different fluid domains. Let us select cap 1, that is the inlet of cold water, and we'll see this one from XY plane. You can see one diamond shaped object is indicating the location of cold water, and we need to push that diamond shape inside this cross flow heat exchanger to indicate the location of cold water, and that diamond shape can be put inside by offsetting the value of x in the positive direction. Let us point the value of x equal to 250. Now you can see the diamond has moved little bit of inside, indicating the cold water inlet domain. You can see it clearly by inserting clipping planes. It is showing that diamond has moved inside, which is indicating the cold water domain. You can rotate this one and see clearly. So this is the cold water domain, right? We can identify this one as cold water region. It is identified. Next to that, we need to identify hot air inlet or hot fluid domain, that is located at cap 2. Let us select cap 2 from here, and we need to identify the location of hot air. Let us change the clipping plane and you can see it. This is the location of diamond. That diamond should be pushed a little bit of inside to indicate the domain of hot air, and that should be put in the negative direction of Z, right? We'll do this one using offset method, and value of Z should be moved inside. It will be, let us say, value of Z equal to minus 120. The diamond has gone inside. Let us check it with different clipping planes. You can see the location of diamond, which is indicating hot air domain. We can move this one little bit up outside to have a better location of hot air domain. Let us make this value as minus 70. Fine. So this is indicating the location of hot air. As we will be providing hot air from sideways, let us update this region, and we can rename this one as hot air region. Let us identify this region. Next to that, we need to identify void domain, which is needed to restrict the flow of fluid from inside to outside. The void domain will be outside this geometry. Let us identify region type as void. We will define location using offset method. For that, let me select the whole geometry. The location of the diamond should be moved away from this geometry, and it is indicated by offset value of y. Let us find offset value of y equal to 2000. You can see diamond has moved outside this domain, which is indicating the location of void domain. We can rename this one as void region. Let us identify this region. We have created 3 different domains: hot fluid domain, cold fluid domain, and also void domain. Excluding that one solid domain will be created by default. As it is a heat transfer analysis, we need to consider solid domain also. Next to that, we need to define leakage threshold. In our case, we are not having any kind of leakage, so we can update with no leakage conditions in our region. As I told before, you can see 4 regions are there. 3 regions we have created, and by default 1 region is produced, that is solid region. Here it is showing void, that to be converted as solid, and we're having 2 fluid domains. One is cold water and another is hot air, and excluding that we're having void region. That one we need not consider. This is required to mesh different sections with different type of meshing. In this case, we'll consider all the meshing criteria to be filled up with polyhexagon meshing, right? So we're considering solid zone as polyhexagon meshing. The solid zone, which is named as circular profile cross flow heat exchanger, and in that case we'll be considering polyhexagon mesh. The remaining cold water and hot air region also should be selected with polyhexagon mesh. That is the best option. Let us update this region. Next to that, we need to select default meshing control options and update. Now we can generate surface mesh with the mesh target skewness of 0.8, and from advanced options we need to select separate contact pairs to be made on, so it will be yes, and let us give global minimum size as 5, and let us generate surface mesh. Surface mesh is being generated. You can see here surface mesh is generated, and you can see the quality. And in our case, we are having average skewness as 0.0319 and maximum skewness is 0.799. And left hand side, we can see that we got different boundaries like cap 1, cap 2, cap 3, etc. That means different entries, inlet and exits. By the same time, we've got some kind of walls, and these walls will be required for heat transfer by convection, right? Let us update these boundaries. Next to that, we need to add boundary layers. In this case, we are considering only 2 boundary layers, so we'll reduce numbers of layers from 3 to 2. Let us add boundary layers. Boundary layers are added. Next to that, we need to go for volume mesh generation, and in this case we're considering quality improvement limit to be 0.04, and let us generate volume mesh. Volume mesh is generated. You can see here, to have a better view of this volume mesh, we can see from clipping pins. You can see the quality of mesh from clipping pins. You can see this clipping pin from right view. Even you can see it from front plane also. This is from top plane. Let us view this one from other plane. overall summary tells that quality of mesh less than 0.1 is 3043 and quality of mesh less than 0.04 is 126. Minimum quality is 0 and cell count is 1.3 million. Next to that, we need to switch on to solution mode. Mesh quality is not good enough. It is okay. We need to refine the mesh. But for simplicity in analysis, we'll move on with the existing mesh. While starting this solution mode, initially we need to fix the units. Let's consider length will be in millimeter and temperature will be in degree centigrade. Close. It is a steady state analysis and gravity will be involved. The direction of gravity will be y as it is indicated by this green arrow in the y direction. So gravity is minus 9.81 meter per second square. Next to that, we need to select models. And as it is a heat transfer analysis, so energy equation should be on. It will be Capsulent to turbulent model, realizable and scalable wall functions. Next to that, we need to provide materials. Two different fluid domains are there. Let us provide fluid from here. It will be water that can be taken from Fluent database. And solid material we are considering as copper. Copy, close. So we have selected materials. You can see here fluid is air and water and solid is aluminum and copper. We'll be considering only copper. Aluminum by default it is provided, but our solid is copper. Next to that, we need to define cell zone conditions. That means we need to define fluid and solid domains. We're having two different types of fluids that we define here. First opening, it will be having water at a lower temperature. So apply and close. Second one, it will be preheated air at a higher temperature of 650 degrees centigrade. Temperature will be provided while applying boundary conditions. At this moment, we should apply the domains only. It will be made up of air. Apply and close. Then we need to define solids. Material we are considering as copper. Apply and close. Materials have been defined. Next to that, we need to apply our boundary conditions, right? So we are having two different inlets. One is water at 10 degrees centigrade and another is preheated air at 650 degrees centigrade. Initially, we will apply water at 10 degrees centigrade from inlet 1 or cap 1. And velocity we will consider as 0.01 meter per second. And temperature, it will be 10 degrees centigrade. Apply, close. Second case, you have to apply preheated air at a temperature of 650 degrees centigrade. And in this case also, we will keep the same velocity of 0.01 meter per second. And temperature, it will be 650 degrees centigrade. Apply and close. It is having two outlets. Cap 3 is the outlet of cold water. Both the outlets will be having 0 gauge pressure that to be applied. Cap 3 is cold water exit. It is having 0 gauge pressure. Let us apply and close. And next one is exit of preheated air. That will also be having same pressure, 0 gauge pressure. Apply and close. And next to that, we need to see the walls. We are having a lot of walls. Let us see one wall. All the walls are made up of copper, and from these walls it will be transferred by convection with a specific convective heat transfer coefficient. Let us consider convective heat transfer coefficient to be 20 watt per meter square degree Kelvin and at a temperature of 30 degrees centigrade. and we are considering wall thickness to be 0.01 millimeter. Let us apply and close. The same boundary conditions to be applied for the remaining walls. So what we'll do is we'll copy this boundary condition and that to be applied for the remaining walls. Let us copy this one and that to be copied to the remaining walls. Let's copy it, and same boundary condition is applied to the remaining walls. It is done. Close. We need to do another thing, that is from cell zone conditions. You can go back to cell zone conditions. From the cell zone condition, we need to select operating conditions. This is needed to prevent backflow. We'll select specified operating density. Let us agree to that one. Done. All the boundary conditions have been applied properly. Next to that, we need to select methods. As it is a heat transfer problem, we'll select coupled method, and from here Green Gauss node based method, and momentum will be second order upwind. Turbulent kinetic energy will be again second order upwind. Turbulent dissipation rate will be also second order upwind. Done. Next to that, we need to start initialization, and we'll consider hybrid initialization. Let us initialize. You can see here hybrid initialization is done. Next to that, we need to run calculations, and in this case we'll consider 100 numbers of iterations. Let us calculate. Iterations have already started. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. Right? Calculation is complete. Now we can see our results, and results can be viewed from here. Initially, you want to see results from reports, surface interiors, and it will be facet average. And you want to see mainly temperature distribution through the exits, right? We know that in this analysis of cross flow heat exchanger, from one inlet we have provided cold water at a temperature of 10 degrees centigrade, and from sidewise we have provided preheated air at a temperature of 650 degrees centigrade, and we're going to have temperature at the exits of cold water and preheated air also, right? That will be obtained from cap 3 and cap 4. And to that, we're going to see the input values also, that is inlet cold water and inlet hot air also, that will be seen together. By the same time, we're going to see some other things like average temperature of cold region and average temperature of hot region. Both the things you can see, right? Let us compute. It is showing here that cap 1, that is inlet of cold water, is having temperature of 10 degrees centigrade, and cap 2 at the inlet of hot air temperature was 650 degrees centigrade. This was determined by the boundary conditions. Now at the exit of cold water, we can see temperature is 26.91 degrees centigrade, and at the exit of hot air it is 267.91 degrees centigrade. That means we can say that cold water has gained a huge amount of heat, and its temperature has risen from 10 degrees centigrade to 26.9 degrees centigrade, and similarly heated air has lost huge amount of heat, and that's why its temperature has come down from 650 degrees centigrade to 267.9 degrees centigrade. Next to that, we're going to see the distribution of pressure, temperature, etc. through different planes. By the same time, to see different conditions of temperature and pressure also, right? By the same time, you can see velocity distribution also at different ends. Let us see velocity distribution also. Instead of pressure, what is the velocity distribution at different locations, right? It's showing that at cap 1, velocity is 0.01 meter per second, and cap 2, that is the entry of hot air. Both the cases we have provided fluids at same velocity of 0.01 meter per second, but at the exit we are having different velocities. You can see the exit of cold water is having velocity of 2.6 meter per second, and exit of hot air is having velocity of 0.024 meter per second, right? And at the boundaries, zero velocity, right? Let us close it. Next to that, we're going to see different continues of temperature and pressure, right? Let us close these things, and we're going to see these results in a bigger way. Let us close this. First of all, we're going to see continues of temperature at different locations. It will be temperature distribution, and we're going to see temperature distribution through cap 1, cap 2, cap 3, cap 4. That means through inlets and exits, we want to see temperature distribution. And let us see hot water inlet and hot water outlet also. Throughout all these regions, let us see temperature distribution. Let us display. It is showing temperature distribution. Here we can see clearly. At the surfaces, you can see these are the temperatures. This is the inlet of cold water, and this is the exit of cold water. Similarly, this is the inlet of hot air, and this is the exit of hot air, right? If we want to see inside, all the things we can see also, like heated zone also, we can see hot zone and also cold zone. Let us see. It's showing temperature distribution inside, distribution of pressure through different planes. You can see distribution of pressure at different planes, right? Downside we are having higher pressure, and upper side we are having little bit of less pressure. Similarly, as cold water is flowing from left hand side to right hand side, you can see downside it is having higher pressure, and top side it is having lower pressure, right? Let us see velocity distribution also through these specific planes. Velocity distribution through this plane number 11 and 12. Let us display. You can see velocity distribution through these different planes, right? And at the exit only it is having higher velocity, right? Similarly here also, at the inlet also we are having different velocity distribution. Next to that, we are going to see distribution of flow particles through path lines, new path lines, particle variables, and you will see distribution of flow particles through the whole cross flow heat exchanger. Let us see. We can see here at the inlet and exit of cold water, we are having similar distribution, but from the sideways when we are providing preheated air, in that case we are having different types of distribution. We can see these things in the form of an animation. Let us pulse it to see the distribution of flow particles. You can see here how different fluid particles are moving from different sides. It is showing dynamics of flow particles. That means how different flow particles are moving from different sides. Let us stop it. Close it. Next to that, we want to see mesh distribution through this cross flow heat exchanger. We don't want to see edges and nodes, we want to see only phases. through this whole cross flow heat exchanger. Let us display. This is the faces of this cross flow heat exchanger, right? Finally, we want to create a scene in between this mesh and also different contours of pressure and temperature, etc. Let us close it. So we have to see scenes, and the scene will be in between mesh and also contours of pressure. And for this one, what we'll do is we'll make the mesh to be transparent. First one, you see in between mesh and contour 1. Let's make the mesh more transparent, so we can see here very clearly. This is between contours of temperature and mesh. With this one, we'll conclude our today's analysis. It's a very simple CFD analysis of fluid flow through a cross flow heat exchanger. In this analysis, we have provided cooled water at a temperature of 10 degrees centigrade from one inlet, and for sidewise we have provided preheated air at a temperature of 650 degrees centigrade. And finally, we saw that the temperature of cooled water has risen by huge amount. With this one, we'll conclude our today's analysis. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.